Hi, this is Tzvi Rosen. Welcome to the first lecture in our online matrix theory course. Today we're going to start by looking at an application of matrices to solving systems of linear equations. And this follows Anton Rorres' section 1.1 and section 1.2. So you can look there for further details. But for now, I'll try to give some motivation and explain how matrices can help us tackle these problems. Let's get started. First of all, what is a linear equation? So a linear equation is something of the type a1x1 plus a2x2, etc., plus anxn equals b, and these are the variables in this equation. The unknowns are x1 through xn. The constants are a1 through an and b. So we can think about these as just any random real numbers that we want to use. So these are numbers. And these variables are the unknown. We're going to imagine that they could occupy any value. Okay? They're not fixed in this problem. And a linear equation can be homogeneous or inhomogeneous depending on the value of b. So if b equals 0, that means we're looking at a homogeneous equation. Whereas if b is not equal to 0, the equation is inhomogeneous. And the way we deal with those different types of equations are a bit different. What do we mean by solutions to linear equations? Well, these are values that we can assign to the numbers, to the unknowns x1 through xn, so that the equation remains true. Okay, and just to give a quick example of that, if we have x plus y equals 1, okay, and obviously I'm not using x1 and x2 here, the same principles hold no matter what the names for our variables are. So this is a linear equation, and an example of a solution to this equation would be, for instance, 1/2, 1/2. Okay? If we assign the value 1/2 to x and 1/2 to y, the equation remains true. Another solution would be 2 and minus 1. Okay? Plug in x equals 2 and y equals minus 1, and we'll find that the equation remains true. These are examples of solutions to the linear equation. When we talk about systems of linear equations, so this is a finite collection of linear equations of the type we were just discussing. When we talk about a solution to the system of linear equations, must be a solution for all of the equations. Okay. So to do a quick example, borrowing the equation from the last slide, we have x plus y equals 1. And x minus y equals 3. Okay, then if we consider the solutions from the last page, so the candidate solutions that I want to consider, So one of the solutions was 1/2 and 1/2, because that's the solution to the first equation. But when we plug it into the second equation, we see that it's plainly not a solution, because when we plug it in, we get x minus y, 1/2 minus 1/2 equals 0. And then on the right-hand side of the equation, 3. Since 0 is not equal to 3, this is not a solution. On the other hand, if we take the solution 2 minus 1, which the other solution we had considered, that's the solution for the first equation, and when we plug it into the second equation, 2 minus -1 is 2 plus 1, or 3. So this is a solution to the system of equations. Okay. So let's continue with these two variable examples, just to get some practice. So how would I find the solution, or the full set of solutions, let's say, to this system of equations? Okay, I want pairs of values x, y, which I sometimes call points x, y, thinking about them in the real plane. So points x, y that satisfy both of these equations. So one approach to doing this is the method of substitution. Okay, so from equation 2, so this is 2, this is 1. From equation 2, if I move the minus 2y to the other side of the equation, I obtain x equals 6 plus 2y. Now I can substitute that value for x into the first equation. Okay, so that means that 1 can be restated as 3 times 6 plus 2y plus y equals 4. Now this is an equation in one variable, so we can solve for that variable. We have 18 plus 6y plus y equals 4. And that gives us 7y equals minus 14. And dividing both sides by 7, we obtain y equals minus 2. Plugging into the original substitution, we get x equals 6 plus 2 times minus 2, which is 6 minus 4, or positive 2. Okay? And another way of interpreting this is graphically. So let's think about how to graph these solution sets here. Each of the equations represents a line in the plane. And the point where both equations have a solution is where the lines intersect. So if we 2, 3, 4. So if we graph these lines, looking at the first line, we have 3x plus y equals 4. So the y-intercept where x equals 0 is 4. And the x-intercept where y equals 0 is 4/3. Okay, so the line looks something like this. Oops. Let's try one more time. Nice. And the second line, so this is line number 1. The second line, x minus 2y equals 6, has x-intercept, when we set y equals 0, x equals 6. And the y-intercept where x equals 0 is negative 3. Okay, so taking the line connecting these points looks something like this. And this point of intersection is exactly the point that we found using algebraic manipulation, which is 2 minus 2. Okay? And so that is the unique solution to this system, because it has to be on both lines. There's only one point where both of those lines meet. Let's consider another example with two variables. Okay, here we have x plus 2y equals 4 and 3x plus 6y equals 6. Well, thinking about using the same approach, if we have, if we would like to substitute, looking at this first equation would probably be easier because we have x all on its own. So let's plug in x equals 4 minus 2y. That comes from equation 1. And we can substitute that into the second equation. So we have 3 times 4 minus 2y plus 6y equals 6. Well, when we multiply this out, we get 12 minus 6y plus, apologies, yes, okay, 12 minus 6y plus 6y equals 6. And here we run into a problem because this means that 12 equals 6. We know this is impossible. But the only thing we did was assume that both of these equations are true. So it must be the case that these equations describe lines that do not intersect. And indeed, they do describe parallel lines. Let's draw the graph to verify that. So we have x plus 2y equals 4. So thinking about the x-intercept, that's going to be x equals 4. And the y-intercept is going to be y equals 2. That's for line 1. Apologies. We'll eventually get this drawing lines thing down. For number 2, so when we plug in y equals 0, we get x equals 2. This is line 1. X equals 2, and when we plug in x equals 0, we get y equals 1. So we get this line. And these are two parallel lines, so they don't meet anywhere. Okay. That means that this system of equations has 0 solutions. And we'll look at one last example of two variables to see another case that can happen. And this is similar to the last pair of equations with one small change. Instead of 6, we have 12 here. And you might be able to guess what happens if we tried the same thing. So we'll substitute 1. We have x equals 4 minus 2y. And we put that into 2 to obtain 3 times 4 minus 2y plus 6y equals 12. Then we obtain 12 minus 6y plus 6y equals 12, which means 12 equals 12. But this is true for any value of y. This implies that any value of y can be a solution, or can be part of a solution. Okay. So if we take any pair of values that looks like, let's say we set y equals t, where t is just any number, and x equals 4 minus 2t, because that's the relationship that they have, then these should be a valid solution to this pair of equations. And the reason for that is that these two equations describe the same line. Okay, so again, 1, 2, 3, 4, 1, 2. So this is the line corresponding to equation 1. And it's not hard to see that it's the same line which corresponds to equation 2. You just multiply both sides of the equation by 3. So this is the same line. And when you have two equations describing the same line, that means that any point on that line will satisfy both equations. So any point is a valid solution, which means that here we have infinity solutions to this equation. Okay? So to review what we found in these few examples, in the case of two variables, we can have one unique solution, and this is when lines intersect. Two, we can have 0 solutions. And this is the case of parallel lines. Oops. And we can have infinity solutions in the case of identical lines. Okay? And this is actually true in general, so it's not just for two variables. Even with linear equations in a higher number of variables, you're either going to have one unique solution, 0 solutions, or infinitely many solutions. Okay. So we've done two variables. Now let's think about three variables. Okay, it's already starting to get a little scary. X plus y plus 4z equals 1, 2x minus 3y minus 2z equals 6, and y minus 5z equals 2. So I gave myself a little assistance here by leaving x out of the last equation. So I can just do a nice quick substitution here using y and z. So for equation 3, we're going to label these 1, 2, and 3. So for equation 3, we're going to take y equals 2 plus 5z, and we're going to sub that into both of the other equations. So this now becomes x plus 2 plus 5z plus 4z equals 1, together with 2x minus 3 times 2 plus 5z minus 2z equals 6. Okay, simplifying, we obtain x plus 9z, and then I want to move the other, so there's no y's anymore because we substituted out the y. I want to move the constant term to the other side of the equation, so we get minus 1 here. And then in the next line we have 2x minus 6 minus 15z minus 2z. So that means we have 2x minus 17z. And then the minus 6 can go to the other side of the equation to become a positive 12. And now we have an equation in two variables. And so we can use the same tools that we did in the last problem. I'm going to sub in using x from the first equation. So let's do a substitution. From equation 1, we have x equals minus 9z minus 1. And we sub this into equation 2, which gives us 2 times minus 9z minus 1 minus 17z equals 12. Okay, simplifying, that means that we have minus 18z minus 17z, so that's minus 35z minus 2. So I'm going to put the minus 2 to the other side of the equation to get 14. And we obtain z equals minus 14 divided by 35. Okay, now applying that to the substitution here, we have 14 times 9 is 90 plus 36, which gives us 126. Okay, so that's 126 over 35 minus 1, which is 35 over 35. So we get, believe it's 89 over 35. And leave a comment if I'm mistaken. And plugging the z into y as well gives us 2 plus 5 times z, which is minus 14 over, oh, you know what, there's a common factor of 7 here. Let's simplify. So this is minus 2 over 5. Okay, minus 2 over 5, that's better. And then we can be more certain when we say that x equals 18 over 5 minus 1, which is 13 over 5. And then y equals 2 plus 5z, which is 0. That's convenient. OK, so as you can see, with 3 variables, things start getting really messy. Like, there's just a lot of work to plug things, figure things out, substitute one thing into another. It starts to feel like you're building a Jenga tower. So we want to try to figure out a better way to do things, right? Because the more variables we put in, the more problems we seem to have. So what's needed is a systematic approach that will work for any number of variables, and most importantly, that you can program into a computer. Okay? And that's where matrices come in. And the tool that we're going to use is Gaussian elimination and Gauss Jordan elimination on the augmented matrix associated to a system of equations. Okay, so there's a lot to define there before we can understand how to use this tool and how to apply it. We have to know what an augmented matrix is. We have to know how to do Gaussian elimination. So let's go for it. The first thing is the augmented matrix. The idea is to put all of the information from the system of equations into a grid of numbers, which is what we call a matrix. We manipulate the grid, and then we convert back to equations afterwards, and the equations will, at that point, will be simpler to solve. So how do we do this? It's really simple. You basically line up variables in columns and the constants on the other side of the equation, and then you just take all of the coefficients. So I have 1 and 2 as the coefficients of x in the first 2 equations. The last equation has no x, so I put a 0 there, because it's if x is multiplied by 0. Next, I have 1 minus 3, 1. Next, 4 minus 2, 5. And now I take the constant terms, 1, 6, and 2. You'll see some textbooks where they put a line here, but I don't think they do that in our textbook, so we'll ignore that. So now we have an augmented matrix. This is the augmented matrix associated to our system of equations. And now we want to know what manipulations of the grid, this grid of numbers, this matrix, will be legal so that it will actually help us solve the system of equations. And those are the elementary row operations. And the reason these work is because they correspond to things that don't change the set of solutions for our system of equations. Okay, so the first elementary row operation is to switch rows of a matrix. And the corresponding thing that you're doing in the system of equations is switching the order that you're listing the equations. And obviously, doing the equations in a different order doesn't affect the set of solutions for it, so that's legal. Another thing you can do is you multiply a row of a matrix by a non-zero constant, and clearly that's something you can do also in a set of equations, right? If you scale the equation, then the equation still, all of the solutions are still solutions of that equation. You've just multiplied both sides by a constant. Another thing you can do, which is a little trickier, is to add a multiple of one row to another row. Okay, and what you're doing there is you're adding multiple of one equation to another, but because you're adding things that are equal to things that are equal, what comes out of that is still equal. So your solutions will still be solutions. Okay, and let's just illustrate how these work. So the first row operation we can take, so let's label these as R1, R2, and R3. So if we wanted to swap R1 and R2, that would be legal. So we could do 0, minus 1, 3, minus 2, 6, 2, 4, 1, minus 3, 2. And the last row would remain the same, minus 4, 5, 1, 0, 2. Okay, so this is what we would get if we swap row 1 and row 2. Okay, how about an example of the second operation? So again, we're going to start with the top matrix here, not the second matrix that we did. So we'll do a scaling. Let's take row 3 and divide it by -4. So we'll have a 1 in the first entry. Okay, so now the first two rows are going to stay the same. And now I'm dividing this by -4, so I'll get 1, and then minus 5 over 4, minus 1 over 4, 0, and minus 1/2. Okay, this is what we get when we multiply minus 1 over 4 by row 3. Again, we'll make a little room here. Okay. And finally, we're going to do the most complicated one. We're going to add twice row 1 to row 3. Okay. And the nice thing that'll happen as a result of that is that this minus 4 will become 0, right? So we have 2, 4, 1, minus 3, 2, 0, minus 1, 3, minus 2, 6. And now we're multiplying the entries of the first row by 2 and adding them to the corresponding entries in the third row. So we have 2 times 2 minus 4 is 0. 2 times 4 plus 5 is 13. 2 times 1 plus 1 is 3. 2 times minus 3 plus 0 is minus 6. 2 times 2 plus 2 is 6. Okay, and so this is what you would get if you take twice row 1 plus row 3. And you put it here. Okay, so these are examples of carrying out each of these row operations. And these are legal moves that don't change the set of solutions that would come out of the augmented matrix. Okay, so now that we know what we can do to a grid, what do we want to do to this augmented matrix? So what form would be particularly nice to get our augmented matrix in for converting back into a system of equations? Well, the easiest thing to have at the end of the day would be a set of solutions. So the idea would be to have something like x equals 1, y equals 2, z equals 3, and then you'd be done. Well, what does that correspond to in terms of the matrix? That corresponds to the system where you have a 1 in the x column, but then that's the only place where x appears. Okay, I'm going to have 3 spots here because it's 3 equations. And then you're going to have the second column will only have a 1 in the y place, and the third column will only have a 1 in the z place, and then you'll have 1, 2, 3 here. Okay, so this is an example of reduced row echelon form. But it's a very special example because you only have columns where there's 1s and 0s. And that's not possible in general. We'll see why in a moment. But the idea here is that you have leading 1s. Okay. So that, for instance, you don't have to take like 2x equals 1. Like you've already cleared the coefficient of the x, so it's just x equals something. Okay, that's one feature. Another feature is that whenever you have these leading 1s, there are zeros everywhere else in the column. So if you have a solution for x is not going to appear anywhere else in the system. Okay, so zeros above and below the leading ones. And what else do we have? So in this example, we don't have any 0 rows. But if we did have 0 rows, we would kind of want to be able to ignore them. So we would put 0 rows at the bottom. OK. So why isn't it possible just to get this beautiful diagonal form all the time? Well, the problem is that sometimes our systems are not just x equals this, y equals that, and z equals that. Sometimes we have parameters, like in the example we saw before with infinitely many solutions. So you could get something that looks like 1, 2, so let's say 0, 0, 0, 0, 0, 0. Let's put a 1 here, and then a 3 here, and a 4 here, and let's put one more row. Why not? 1, 5, 7, and you know what? Let's get a 0 row at the bottom. And another few entries, 3, 6, 8. OK, beautiful. So what does this correspond to? Well, let's say that the names of the variables here are a, b, c, d, e, f, g. What we have here is the following system of equations. If we were to translate this out, we have a plus 2b plus f equals 3, c plus 3e plus 5f equals 6, and d plus 4e plus 7f equals 8. Okay, and then we have 0 equals 0 at the bottom. We can kind of ignore that. And in this system of equations, E and F have a special situation. So there are different roles for A, C, and D, and B, E, and F. Okay, so A, C, and D, these are called leading variables because they correspond to the leading ones in these rows, right? So because they correspond to the leading ones, they're called leading variables. And they'll appear exactly once in each of these equations with coefficient 1. On the other hand, B, E, and F are called free variables. And they can appear multiple times. And they can be treated kind of like parameters, right? So the way that we had substituted in t when we were describing that line, these also can be considered like t. They're variables that you can pick their values freely, and then they'll determine the values of the leading variables. Okay, so these can be chosen freely, then determine the leading variables A, C, and D. Okay, and you can see why that would be true, right? So let's say I pick variables for B, E, and F. Okay, now all of these terms become constants. And now it's a simple equation that tells you the values of A, C, and D. Okay? So that's the function of leading and free variables. That's why we're not always going to get this nice diagonal form 1, 1, 1, because you might have some free variables thrown in there. Okay, so let's summarize what we want in reduced row echelon form. So the first thing is that non-zero rows start with a leading 1. Okay. The 0 rows are at the bottom. We mentioned that, though it won't come up if you have the right number of equations, or if none of the equations are redundant. This point is one that I didn't mention. But basically, you want to have your equation for the earlier variables come first. So you want to put x equals, k before y equals L. Okay, and if it's not that way, then you just switch them. Okay, and the picture here is just to have 1, and then maybe some other numbers, and then 1 down here. So your rows, the leading ones, should be moving down and to the right, not up and to the right. Move down to the right. Okay. And finally, columns with leading 1s are otherwise 0. So those leading variables only appear once in your system of equations. Okay. How do we read off the solutions from the rref, the reduced row echelon form? So let's take this example. So as I mentioned, we have our free variables and we have our leading variables. So we can choose parameter names. Let's say we want T1, T2, T3. Okay, then we'll have T is always our parameter. Okay, so T1, T2, T3. Okay, and these are going to represent arbitrary numbers. So the solutions here, well, I can arbitrarily set parameters for B, E, and F. So I'm going to take T1 to be B. Okay, and then I have C and D. This leaves a little more room for A, C, and D. So T1, C and D. And then E and F will be T2 and T3. Okay, and now let's plug that in into these equations, and we can read off the values for A, C, and D. So in the first equation, I have A plus 2B is T1 now, plus T3 equals 3. So that means that A will be equal to 3 minus 2T1 minus T3. Okay. And that's just rearranging the equation. C plus 3E is T2 plus 5F is T3. It's going to be equal to 6. This represents that this corresponds to C being equal to 6 minus 3T2 minus 5T3. And then D is going to be equal to D plus 4, again, E is T2, plus 7T3 equals 8, tells me that D is equal to 8 minus 4T2 minus 7T3. And that's exactly what we can plug in here for the corresponding solutions. So we have 3 minus 2T1 minus T3, 6 minus 3T2 minus 5T3, and 8 minus 4T2 minus 7T3. Okay, and this is a valid solution this actually describes the full set of solutions to this system of equations. Okay? And that's how we get from the reduced row echelon form without much difficulty to the solution set for our system of linear equations. Okay, well, we can be a little laxer about reduced row echelon form versus, we don't have to go all the way with reduced row echelon form. There's kind of an easier path, which is the row echelon form, meaning it's not reduced. Basically, instead of doing the step where I clear the columns that have ones in that have leading ones in them, so I could, for instance, take 4r2 plus r1, and I would get 1, 0, 14, and 0, 1, 3. So the other thing I could do is I could just say, you know what, this is my row echelon form, and now this is reduced row echelon form, and I could read off from that x equals 14, y equals 3. Instead, I could say, you know what, this is fine as is. I have x minus 4y equals 2 and y equals 3. And now I could just substitute y into the previous equation. Well, y equals 3, so this is x minus 12 equals 2, so that means that x equals 14. Okay, so the claim here is that it's approximately as easy to solve row echelon form matrices as it is to solve the reduced row echelon form. Okay. So now we know how to manipulate matrices. We do elementary row operations, and we know the matrices that have the easiest form for us to interpret as solutions of the equations, and that's the reduced row echelon form or the row echelon form. And so the process of using those elementary row operations to get to row echelon form is called Gaussian elimination. And here's how it goes. In general, you start from the top left, and you scale the row, meaning you multiply by a constant, so that the leading entry is 1. And then you add multiples of that row, the top row, to the rows below, so that those entries are 0. And then you move diagonally down and to the right and repeat. Okay, so scale it so that the first non-zero entry is 1, and add it to the lower ones. Okay, so if the top left of whatever part of the matrix you're looking at is 0, you want to switch rows so that it's not 0, and then you can scale it to 1. But if there's no row like that, if the whole column is 0, then you just go to the next column. Okay, you can leave that column as 0 and you're fine. Okay, and that's basically Gaussian elimination. Okay, so let's do an example of Gaussian elimination. We have a system of 4 equations, right? We had a tough time with doing 3 equations before, now we're doing 4. Let's go for it though. We have x minus 2y plus 2z minus w equals 3. So we're going to go straight ahead and translate to the augmented matrix. Okay, so what is that in our case? We have 1 minus 2, 2 minus 1, 3. Okay, that's the top row. Then we have 2, 1, minus 1, 2, 2. And we have 1, 0, minus 1, 1, 1. Okay, these are our 3 equations. This is our augmented matrix for the system of 3 equations. Okay, so the first thing we want to do is start at the top left and scale it to 1. We're actually in luck. It's already 1. Okay, so the next step, okay, so first scale top left to 1. Okay, this is done. Okay, the next thing we want to do is use multiples of that first row to get rid of the elements below it. Okay, so add first row to lower rows to make entries 0. Okay, so we're going to need to borrow this matrix and do that on the next page. Give ourselves a bit of space. Okay, so to get the first entry of the second row to 0, we would need to add -2 times the first row. So that's what we're going to do, -2r1 plus r2. And to get the third row to be 0, we would need minus the first row, minus r1 plus r3. And that's what we're going to do. We're going to do both in this one iteration since they don't affect each other. So we have 1 minus 2, 2 minus 1, 3. And now adding minus 2 of the first row, we get 0. And minus 2 times minus 2 is 4. So this becomes 5. Minus 2 times 2 is minus 4 again. That's minus 5. Minus 2 times minus 1 is positive 2. That gives me 4. And then minus 2 times 3 is minus 6, plus 4 is minus 4. Okay. And then we have minus r1 plus r3. So minus 1 plus 1 is 0. Minus negative 2 is 2. Plus 0 is 2. Minus 2 plus minus 1 is minus 3. Minus minus 1 is 1. Plus 1 is 2. And minus 3 plus 1 is minus 2. OK. So far, so good. So now we have this first column, and it's completely 1 followed by zeros. So we're happy with that first column. And now we move down and to the right. OK. And so now we want to scale this second row so that the first entry is 1. Okay, so we have to multiply the row by 1/5. Okay, so we have, let me signify that I'm doing that over here. Okay, that'll do it. We're going to signify that here. So we're doing this 1/5 times r2. And we put that here. So the first row doesn't change. We get 1 minus 2, 2 minus 1, 3. Now we're multiplying the second row by 1/5. So we get 0, 1, minus 1, 4/5, minus 4/5. And the third row doesn't change. We get 0, 2, minus 3, 2, minus 2. Okay, and so now we have to take a scaling of the second row, add it to the rows below so that the entries below are 0. Okay, so we're going to take minus 2 times that second row and add it to the third row. And we obtain, okay, first row stays the same, second row stays the same. Oops. And then third row, we're adding minus 2 times the second row. So it's minus 2 times 1 plus 2 is 0. Minus 2 times minus 1 is 2, plus minus 3 is minus 1. And then minus 2 times 4/5 is minus 8/5. Plus 2 is positive 2/5. And then minus 2 times minus 4/5 is positive 8/5. Minus 2 is minus 2/5. Okay, and now to do the final step of the Gaussian elimination, I need the last row to have a leading 1, so I just take the minus of it. So we have minus r3, and we obtain 1 minus 2, 2 minus 1, 3, 0, 1, minus 1, 4/5, minus 4/5, 0, 0, 1, minus 2/5, 2/5. Okay? And now if we want to take this and turn this into a system of equations, what we have is a minus 2b plus 2c minus d. Oh, sorry, no, we started with variables. These are x, y, z, w. So let's use those. X minus 2y plus 2z minus w equals 3. Then we have y minus z plus 4/5 w equals minus 4/5. And z minus 2/5 w equals 2/5. Okay? And taking this system of equations, I can set w as our parameter, so I'm going to take it to be t just so we have some consistency there. Right? Because all of these are the leading variables. X, y, and z are our leading variables, and w is a free variable. So plugging in w equals t, I can solve for each of the free variables. So we have z is now going to be equal to 2/5 plus 2/5 t. Okay, now if I plug that into the second equation, I get, so let's sub that into 2. We get y minus 2/5 plus 2/5 t plus 4/5 t equals minus 4/5. Simplifying this, we have y minus 2/5, then minus 2/5 t plus 4/5 t is plus 2/5 t equals minus 4/5. And then moving everything to the right-hand side besides y, we get y equals minus 2/5 minus 2/5 t. Okay. And subbing both those values, or all three of those values, into equation 1, we obtain x minus twice negative 2/5 minus 2/5 t plus twice 2/5 plus 2/5 t minus t equals three. Okay, and so what we find is that we have, well, it's minus 2 times minus 2/5 minus 2/5 t, and then plus 2 times the positive of that. So it's actually just plus 4 times 2/5 plus 2/5 t. So this is plus 8/5 plus 8/5 t minus t equals 3. Okay, and this gives us, moving everything over to the other side, we get x equals 3 minus 8/5 is 7/5. And 8/5 t minus t is 3/5 t. So we get minus 3/5 t. Okay, so taking these values that we got for each of the variables, so x equals 7/5 minus 3/5 t, y equals minus 2/5 minus 2/5 t, and z equals 2/5 plus 2/5 t, and w equals t. That describes the full solution set for our system of equations. Okay. Just to review what we've done, we did Gaussian elimination to get our augmented matrix into row echelon form. Then we converted back to a system of equations, and we substituted repeatedly to find a form for the solution. Okay, but there's an alternative way to do it, which is Gauss Jordan elimination. And this is going further to get the matrix into reduced row echelon form. And the way that we do that is we start with the row echelon form, and this should be just 1r, and then use the leading ones to cancel the entries above each of the leading ones as well. So let's do that with this matrix, which is the row echelon form that we got before. So to do the Gauss Jordan elimination, we want to eliminate the entries above the leading ones. So the first one to eliminate is this -2. So we can take twice the second row and add it to the first row. What we obtain is, well, the first entry doesn't change. The second entry becomes 0. The third entry, we have -2 plus 2, that's also 0. And then 8/5 minus 1 becomes 3/5. And minus 8/5 plus 3 becomes 7/5. Okay, and now the other two rows don't change. Okay, now how can we get so this entry here is already 0, so we're in good shape there. The only entry above a leading one that we need to eliminate is this one, which I'll highlight in pink, and let's get rid of it. So the way we can get rid of it is by adding the third row to the second row. So we'll do R3, just 1 times R3 plus R2. Okay, and we'll put that in the second row. So the first row stays the same. The second row now becomes 0, 1, and now we add the third row. So this becomes 0, this becomes 2/5, and this becomes minus 2/5. And this stays the same. Okay, and now as you can see, the matrix is in reduced row echelon form, and it can be simpler at this point to read off the solutions, right? We have this corresponds to x plus 3/5 w equals 7/5, y plus 2/5 w equals minus 2/5, and z minus 2/5 w is equal to 2/5. Okay, and so just moving the w's over to the other side gets you your full solution set. So Gauss Jordan elimination takes more steps than Gaussian elimination in the matrix part, but then it saves you time once you're actually solving for the variables. Okay, in summary, what have we done today? We found that systems of linear equations can have 0, 1, or infinitely many solutions. In order to find those solutions, we can translate the system into its augmented matrix. Then using Gaussian or Gauss Jordan elimination, we can transform the augmented matrix into row echelon or reduced row echelon form. And then from the row echelon or reduced row echelon form, we can convert back to the equation form where it will now be easily solved. Hopefully this gives us a taste for how matrices can be used to organize information and help us do computations, particularly using a computer and programming. Okay, well, I'll see you for next lecture. Thanks for your attention.